Welcome to the regression line. So the idea behind here is we want to find a line that best seems to fit the pattern the dots are following. So we want to find the line that best seems to fit the pattern of a scatter plot. So recall with our scatter plot, we had our band that the dots fit in, and the line will more or less just run through that. So the line that best fits a scatter plot doesn't have to go through any of the points on the scatter plot, or it doesn't have to have any of the points actually on the line, but it does show us the general trend that's going on in that band. So this is the regression line. The regression line has multiple names. So all of these are the same thing. We have the regression line, the best fit line, and the least squares line. So all of these are the same thing. So these are all names for the same thing. So the least squares line is actually, or the least squares is actually where the line comes from, how it's calculated. So the general idea here is if we have our scatter plot, and we have a line that runs through our scatter plot, then for each point we have, for any value on the x-axis, so for any value of our explanatory variable, the line tells us what the pattern would suggest would be the response. But then we have at the points things that actually happened, what was actually observed. So each point may or may not fall on the line, and that distance from the line up to the point or down to the point is essentially the error in what the line would predict versus what actually happened for that individual. The least squares line, the idea is we take each of those errors and make a square. And then add up all of those areas. So we find the area of each square. So we find the area of each square. Add up all of the areas. So if we add, whoops. If we add up the areas of each square where the side is the error between the point and the line. Then the least squares line is the line that has the smallest sum or smallest total area. So the least squares line is the line with the smallest total area. It turns out that this line is unique. For each scatter plot, there is only one line that has this smallest possible total area if we look at all the squares based off of the error between the line and each point. So if you find the least squares line and add up all that area, and you find another line and then you pick another line that's different, it will have a larger total area if we add up all those squares. So the least squares line, basically, they're just trying to minimize the square of the errors. The reason they use the square of the errors instead of just the error itself is if the points are close to the line, it's very clear what the pattern is. It's the points that are far from the line that make a huge difference. And so the goal here is we want to have lots of points close to the line and few points far from the line. And when we find areas of squares, if we have small side lengths, the area of a square is very small. Right? If we have a side length 1, the area would be 1. Side length 2, the area would be 4. That jump is not very large. On the other hand, if we look at the distance between, say, a square of side length 9 would have area 81 versus a square of side length 10 would have area 100. Now we jump from 81 to 100. That's a jump of 19 when the error itself only changed by 1. So we want points close to the line. We don't want many points far from the line. So doing the square of each error instead of just the error itself sort of makes the far points have a lot more weight. Our goal is to have most of the points very close to the line, few points far away. So this is why it's called the least squares line, the general idea behind it. That's it. In future videos, we will learn how to find this line in Desmos.